Up to this point, we have been only considering solutions that have a single acid in them. But we're now going to, just for this video here, discuss what we could do if we had a solution with multiple acids in it. And we're going to look at the simplest possible situations where this could happen. There are definitely much more complicated ones that we are just not going to worry about at this point. So the situation that we are going to look at is if we have a mixture of a strong acid with a weak acid. And like I said, this is the simplest possible combination. If you were to have two strong acids, I guess technically that would be simpler. But if you have two weak acids, that is definitely much more complex because they would be messing with each other, essentially. The one molecule producing H plus is going to mess with the equilibrium of the other molecule producing H plus, and it gets messy. It's still doable, but it is messy. If you have a strong and a weak acid, however, we're still going to have one acid messing with the other acid, but it's only a one-way street. So with the two weak acids, the two mess with each other, but if you have a strong and a weak, the strong acid is just so overwhelming in the amount of H plus that it produces that it just completely swamps the weak acid. And so for these mixtures where we have a strong acid and a weak acid, as long as we have any significant concentration of strong acid, we are just going to ignore the weak acid. We're going to pretend like it isn't there, because that strong acid, as long as there is any significant concentration, and by that I mean like anything, even like millimolar, so like 1,000th of a molar, even if you just have that much, that is more than enough to completely swamp the weak acid. And what happens is you have produced so much H plus that the weak acid, its equilibrium gets pushed so far to the left, using Le Chatelier's principle, it pushes it so far to the left that essentially none of the weak acid dissociates. So for these mixtures, we're only going to consider the stronger of the acids. So as an example of that here, we have the pH of a mixture that is 0.15 molar HF and 0.1 molar HClO. Now, in this case, neither one of them is a strong acid, but the HF is so much stronger than the HClO if we look at the Ka values, which I believe we can find. Boy, we might have to scroll back a ways. There they are. So here we have HF, and there's HClO. There's 4 orders of magnitude difference there, and that's going to be big enough that we're just going to look at the stronger acid. Now, if this was a question on a homework or an exam, I wouldn't leave it where it's kind of questionable like it is right now. Like, well, you say it's strong enough, you know, there's a big enough difference. How do we know what the big enough difference is? I would just give you a strong acid. I wouldn't give you two weak ones like this. I would give you a strong and a weak, so there wouldn't be any question. But since I'm here to work this one with you, we'll go ahead and just take the stronger one and say we are not even going to consider the rest of that sentence. So we're just going to say find the pH of 0.15 molar HF. We're essentially treating it like it's not even a mixture at all. And so we would do very similar to what we did in previous video. We would have our little ice table here with our initial change and equilibrium. We have HF, H plus, and F minus. 0.15 is 0 and 0. This is going to decrease. These are going to increase by some unknown amount. leaving us with x, x, and 0.15 minus x. We're going to go ahead and make the x's small assumption, and we'll double check to make sure that it's correct, but I believe it will be. Oh, I should have written down that Ka value. Sorry for flying through the slides here real quick, but so 3.5 times 10 to the negative 4. Okay. So 3.5 times 10 to the negative 4 is our Ka value. That is equal to x squared over 0.15, because again we're making the x's small assumption. And so if we do that math, we get x is equal to 0.007, we'll say 725. We'll just cut it off there. Okay. So then, if we go ahead and check our assumption, divide that number by 0.15 times 100. Ooh, it is really close. It is really close. It's 4.83%. So that is pretty much as close to not being an acceptable assumption as possible. We're going to go ahead and stick with it. And so if we go ahead and stick with that, the pH would then be just the negative log base 10 of the 0.00725. And that is 2.1, well, actually, be 2.14 with well, I guess I could have had 140, yeah, proper sig figs. That would be the pH. Okay. Very similar to that mixture of two acids where one of them is much stronger than the other. And like I said again, I'm not gonna worry about having you memorize like what is the maximum difference that you can have before one acid is considered strong enough that you can ignore the weak one. If I'm giving you a question like that somewhere else, it will just be a strong and a weak acid. There won't be any question. But a similar situation is if you have what we call a polyprotic acid. And polyprotic acids are any acid that has more than one acidic hydrogen. So if you have more than one hydrogen that is able to pop off of the molecule to form H+, then each of those individual hydrogens is going to have their own Ka value. Because when one of them is removed, what ends up happening is all the rest of them have a harder time being removed. They, like for phosphoric acid here, for example, all three of those hydrogens are equivalent. Like there's no difference between them. But when one of them leaves, what's left behind is negative. So it starts off as H3PO4, and after one of the hydrogens leaves, you have H2PO4 minus. So that negative charge actually makes it significantly more difficult for the second hydrogen to leave. And then for the third one to leave, it's even more difficult because like that, the proton just likes that negative charge, like it's attracted to it. So it's more difficult for the second and then the third protons to be pulled off of those molecules. And there's also some resonance stuff and other things going on here. But the main point, the thing that you really need to be concerned with is just that each subsequent deprotonation of the acid is more difficult. And that will always be the case. There's never going to be a case where the first Ka is more difficult. It's more difficult to pull the first one off than it is to pull the second one off. That's never going to happen. And so with these, we're going to have a rule of thumb that if two Ka values are at least 10 to the third difference, so 3 orders of magnitude difference from one to the other, then we can ignore the weaker deprotonations. So for example here, going from the first deprotonation of sulfurous acid to the second deprotonation, there's 6 orders of magnitude difference here, because we have -2 and we have -8. And so because there's such a huge difference here, the first deprotonation is going to be the key one, and we're just going to ignore the second one. If we have this, on the other hand, so citric acid, the first and second deprotonations are actually decently close to one another. So we have 7.4 times 10 to the -4, and then 1.7 times 10 to the -5. They're within roughly, well, actually they're actually well within 1 order of magnitude of each other. And even the third one is actually technically within 3 orders of magnitude of that first one. But I'm just going to tell you right now, that third deprotonation, it's not going to have any effect. Because what these subsequent deprotonations are is the only thing that can go through this second deprotonation are molecules that went through the first one. So very few molecules go through the first deprotonation in the first place. And then you're going to take that tiny number of molecules that went through the first deprotonation and say, oh, okay, only a tiny fraction of those go through the second deprotonation. And so then at that point, you have a tiny fraction of a tiny fraction that are capable of going through an even tinier fraction of those to have the third deprotonation. And so these third deprotonations, they're never going to give us anything. Unless you are doing the most precise work that you will ever do in your life, where you need to know, like, down to the thousands of atoms how many have deprotonated, you're not going to worry about that third deprotonation. The second one sometimes will. Like in this case, especially if you have a relatively large concentration to begin with, the second deprotonation would be significant. But that third one, it's not going to have any effect at all. The second one is relatively small, even in those cases where it is, where you do need to take it into account. So just like as a rough idea of what happens here, the first deprotonation here, maybe you end up with a pH of 4.21, and then when you take the second deprotonation into account, maybe you end up with 4.20. Like it's a very small change. But, you know, that's enough that you would want to take that into account. But then when you take the third one, it's still just going to be 4.20. It's not going to have any effect. And so we just ignore it. So let's do one real quick example here, and then we will call it for this video. So in this case, we are looking at soda water, essentially. So when we buy soda water, which is carbonated water, we're buying a solution of carbon dioxide in water. The solution is acidic because CO2 reacts with the water to produce carbonic acid. What are all three of those concentrations in a saturated solution of CO2 with an initial concentration of 0.033 molar? Okay. So we have two deprotonations that are going to happen here. And like I hinted at in the last slide, we're going to go ahead and do this second deprotonation here just so I can show you that it's not going to have any significant effect. Because if you notice here, they are more than 3 orders of magnitude apart. So if this was on an exam, I would expect you to realize, oh, that's a big enough difference. I don't need to worry about it. Now we're going to go ahead and do it here, just so I can show you I'm not lying. I'm not just trying to be lazy to get out of the math. I'm going to actually show you that it's not going to have any significant effect. Okay, so we're starting with 0.033, and we're going to have none. And I'm just going to call this, instead of writing out the whole molecule, I'm going to have H2A, so the A is the CO3. I'll have H+, and then I will have HA-, because it lost one proton there. The second deprotonation is going to be HA-, H+ again, and A2-. So, for this first deprotonation, we are going to have some unknown amount of that be consumed and produce the same unknown amount of the other two. So we'll have X, X, and then 0.033 minus X. And I'm actually not going to make the X's small assumption here, because if you think about it, what the X's small assumption is saying is that there's no point in even considering the amount of X here. It's just so tiny, so it doesn't feel right to make the X's small assumption. Now in reality, if you make the X's small assumption here, it's not going to have a big change on the end result. But I'm going to go ahead and not make the X's small assumption, because I know I can plug it into my calculator here fairly quickly and solve for an answer that does not include an assumption. So let me do that real quick. Just bear with me while I plug this in. Feel free to play some elevator music on your own computer there. It's -7. Oops. It would be helpful if I put it in correctly. Okay. I think that is correct. Let's see. What does it give me? 1 point tells me that X is 1.19 times 10 to the -4. Okay, so that is X, which means that is what's going to go in here for that second deprotonation. And that means it's also going to go in here, because X is not just the amount of the acid that was deprotonated, it's also the amount of H+ that was produced. And so we're going to have 0 of this to start with, and then it's going to be the exact same process here. So we're going to have, I won't use X again, I'll use Y. So we're going to have -Y, oops, plus Y, plus Y. And so this is going to be 1.19 times 10 to the -4 plus Y, Y, and then 1.19 times 10 to the -4 minus Y. Okay, so once again, I am not going to make the X's small assumption, because that kind of defeats the purpose of doing the deprotonation here. If you're saying it's not going to have any effect at all, then why even bother? So I'm going to go ahead and type this in real quick. Again, I apologize for you just having to sit there and wait for me to plug things in. So we're going to have 1.19 times 10 to the -4. I guess I could write it out so you could see what I'm doing. So I'm doing this. 5.6 times 10 to the -11 is equal to that divided by 1.19 times 10 to the negative 4. Oops, that should have been plus here. Sorry. Plus y up there, minus y down here. Okay. So that plus, and then that again, all of that divided by 1.19 times 10 to the negative 4 minus q. I'm using q for my unknown here. And then that minus 5.6 times 10 to the negative 11. Alright, here's hoping it works. Okay, it gave me a number. Good. So that is telling me that y is equal to 5.6 times 10 to the negative 11. Tiny, tiny, tiny. Now, I actually kind of forgot there for a minute that I did actually need to do the second deprotonation because the question isn't only asking for the pH or the concentration of H+. It actually, one of the things it asked for was this concentration. So we did actually need to do that second one just to find this, to find the concentration of the doubly deprotonated carbonic acid, which is 5.6 times 10 to the negative 11. But for the other two, for the concentration of the singly deprotonated acid and the concentration of H+, if you take 5.6 times 10 to the negative 11 and either add it or subtract it from the 1.19 times 10 to the negative 4, it's still 1.19 times 10 to the negative 4. Like, you did not change that number at all. You would have had to have, let's see, what would that be? 8 sig figs or something like that in your answer. You would have to be that precise to be able to see a difference in the two answers. So those two concentrations are just 1.19 times 10 to the negative 4. All right. I hope that made sense. If not, just let me know and we can talk about it some other time. But in the next video, we will be looking at weak bases and how they compare to weak acids. So I'll see you there.